So today we're happy to welcome Ciaran McCreesh, who will tell us whether our algorithms are really telling the truth to us or not. So please take it away.
So this is joint work with a growing number of co-conspirators at this point. So I work on practical algorithms for finding little graphs inside big graphs and similar combinatorial problems. So a simple problem, subgraph isomorphism. I give you this little graph on the left. The question is, does it occur inside the big graph on the right? And it turns out this is a problem that a lot of people want to solve in practice on real graphs in actual applications. And in this case, yes, we can find a little graph inside the big graph. That is one example. Quite often we want to find all of the matches. So in this case, for example, I could find another match by swapping these two vertices, or I could use that triangle at the top and the edge coming downwards. Are there any more? Have I found them all? So there's also that triangle there with the edge coming down. There is this triangle here with the edge coming up. So those give us another two each way. Possibly some more, possibly some not. But it's fairly easy for me to convince you that any particular match that I show to you is a match. But if I want to say that I'm giving you all of the matches, sometimes this is a more difficult problem. Another problem that people actually want to solve in practice is maximum clique. So you give me a graph. A clique is a subset of vertices where everything in the subset is adjacent to everything else in the subset. And we want this to be as big as possible. I claim in this case that the maximum clique has 4 vertices. So I can show you a 4-vertex clique, and you can easily check that, yes, I'm telling the truth, this is a 4-vertex clique. But if I'm claiming that this is the biggest, I'm going to have to do a bit of work. It's not immediately obvious. And in general, the way I think about these kinds of problems is constraint programming. So in constraint programming, we have these things that we call variables. Each variable has a finite domain. We typically think of these as being a subset of the integers. And we have some constraints between variables. And we want to give each variable a value from its domain, satisfying all of the constraints. And we might have some minimize or maximize objectives, similar to this. And we typically solve these problems using a combination of inference and intelligent backtracking search. These problems are hard in theory. The graph problems are also hard to approximate, hard to do anything that you want to do with them, really. And yet, in practice, we can solve maximum clique on larger graphs than all pairs shortest paths for certain graphs, etc. But the point here is, although these are NP hard somehow, we're still solving them exactly very quickly in practice. And we don't entirely understand why we can get away with doing this. There is a slight problem. The state-of-the-art implementations of solving algorithms for these problems, just occasionally, say 1 time in 10,000, will produce the wrong answer. Now we can say, okay, we're going to test these algorithms really, really thoroughly. The problem is empirically testing only uncovers superficial bugs. That these solving algorithms will use all sorts of kinds of inference, and sometimes interactions between different kinds of inference will misbehave in strange ways. It is really hard to convince yourself that, okay, you have comprehensively tested every way that things can interact, so we can be sure the algorithm is right. And even if I say to you, okay, I have tested this algorithm really, really carefully, should you believe me? Probably not. There are bugs in solvers written by people who have been doing this a lot longer than I have, a lot more work into it. Another example, another thing we could do is correct by construction formal methods. So the idea here is we start off with a mathematical specification of what the program does, and then the computer constructs a program for us in a way that it is guaranteed to conform to the specification. The problem here is this is vastly far away from being able to scale to the kind of solvers that we want to use in practice. So I'm going to try and convince you that there is a third way of doing this. We call this proof logging. So what's the idea? We have an input, we run it on a solver, and the solver gives us a result as before. Except additionally, we're going to modify the solver so that it also gives us a proof. And we're going to take this proof and the input, and we're going to feed it into a proof checker. And the proof checker is either going to say, yes, the proof is fine, or no, there is a problem here. And if the proof checker says, yes, you're okay, then we are absolutely sure that, yes, we have found the legitimate answer by legitimate means. If the proof checker says no, it means there is a mistake in our proof. It doesn't necessarily mean that we've definitely given the wrong answer. It means that we've cheated and we may or may not have reached the right answer. But the point here is if you give the proof checker a valid proof, it will definitely say yes. If you give it an invalid proof, it will definitely say no. So what is a proof? This is, I believe, the world's shortest maths paper. So the claim, a direct search on a very old computer yielded this sum of powers equals this power as the smallest instance in which 4/5 power sum to a 5th power. This is a counterexample to conjecture by Euler. So looking at this, I can check that this equation holds. I can put these numbers into a high precision calculator. I could even do these sums by hand if I really wanted to. I can add this up and I can check. So are we happy this is a proof?
Yes.
The problem here is the smallest. How do we know they haven't missed something? This is where things are a bit shaky. I mean, for modern computers, it wouldn't take very long to run this again, but somehow I am convinced that yes, this is an example. I am not convinced that this is the smallest example.
I'll argue that this is the proof. The conjecture is just that something like this doesn't exist.
Yes. So, okay. Yes. So for the conjecture, this is a counterexample to conjecture. I'm happy with that. But it's specifically the smallest bit that is a bit shady. Okay. Is everyone familiar with SAT? So we have some Boolean variables, true or false. By a literal, I mean a variable or its negation. A clause is saying literal 1 or literal 2 or literal 3 or so on. And I'm going to say, okay, you need to satisfy clause 1 and clause 2 and clause 3 and clause 4 and so on. And the question is there a way of satisfying a given formula? So, for example, this formula here. Okay. Suppose I want to convince you that the SAT formula has a solution. All I need to do is give you the assignment. So I say, okay, set P to true, Q to false, X to true, so on. And it's relatively easy for you to go check that, yes, okay, I have not made a mistake here. Unsatisfiability, so convincing you that there are no solutions. This is the tricky bit. What I'm going to do is I'm going to give you a sequence of clauses, possibly an exponentially long sequence, where every clause follows obviously from what we know so far. So given everything that we know, so starting with the input, and given every fact that was derived so far, I'm going to give you a new fact that is obviously true. And the final step in my proof is going to be an empty clause. So I'm going to have a clause where it says, you've got to set at least one of the following things to true, and I give you no things. So this is a contradiction. Okay. And if I can go through this process and end up with an empty clause, then I've shown you that the original formula is inconsistent. So at every step of the way, I'm giving you something that is an obvious consequence. I'm finishing with a contradiction, so the input is to be the contradiction to begin with. So the question is, what is obvious? And I'm going to start by telling you what unit propagation means. So I'm going to take a clause and I'm going to give you a partial assignment. So I'm going to say, okay, set this variable to true, this variable to false, and I don't know, I'm not telling you anything about the rest. And then we're going to see, okay, what can I do that is immediately obvious when you give me a partial assignment? And here's an example. So I'm going to give you this partial assignment saying set P to false and Q to false, and this is our original formula. So we're going to go through, I've told you that P is false, I've told you that Q is false, and we know that P is true, so not P is okay. And what we see here is we're in two places where we have clauses that only have one thing left in them. So if I have any chance of satisfying this clause at all, I'm going to have to set both of these to true. Okay. In particular, I'm going to have to set U to false because of P being set to false. And once I have done this, let's see, I've got a not Q and an R. So I'm going to have to set R to be true, which gives us something here. We have this W. Again, we're going to have to set that to be true to satisfy the clause. And I believe this is the only thing we do now. So we have finished. So the idea is we're going to look for any clause that only has one thing left that we have to set so that we can satisfy that clause. And we're going to keep doing this until we reach a fixed point and we stop. Okay. We call this unit propagation. And I claim that this is a sufficiently simple thing that a proof checker should be able to do this on its own without us having to help it too much. Okay, suppose we want to actually solve the SAT problem. The original way of doing this is the DPLL algorithm. So the idea is we're going to pick a variable, we're going to guess either true or false of a variable, we are going to unit propagate, and then we're going to recurse. So again, we're going to pick another unassigned variable, set a true or false, unit propagate, and so on. If at any point unit propagation reaches a contradiction, then we're going to backtrack. Okay. So for example, I might decide to branch in a variable x and start by setting it to false. We can see the consequences here. I might set y, decide to branch next on y, and also set it to false. And then we step through the unit propagations. We're going to pick up a z here and a not z here. So stepping through, we get a contradiction. But what I'm going to do whenever we reach a contradiction is I'm going to write down the negation of all of the guesses that I've just made. So I guessed that x is false and y is false. So the negation.
You picked up the unit propagation on U, right?
Yeah.
And then you had the first and the last.
Yeah. So we get a contradiction here, for example. Yep.
Okay.
Yeah. This contradicts in multiple ways. I think it also contradicts on the z. So,
Those are true, right?
oh, those are true. Yes, you're right. Used by my fellows. Yeah, so we have a contradiction on the last clause. Okay, so I'm going to write down the negation of what I guessed. So I guessed that x is false and y is false, and I reached the contradiction. So I'm going to write down, okay, either x is true or y is true. And this is going to be the first step in something that I will call a proof. We're going to backtrack and set y to be true again. And let's see, we're going to get a contradiction. Ultimately, we're going to end up here. So I'm going to write down, again, the opposite of what we're doing. So I'm saying that either x is true or not y is true. Now we backtrack. We're in a state that we have guessed that x is false. And this leads us to a contradiction because if x is false, we have to have both y and not y simultaneously. So that's a contradiction. So I'm just going to write down, okay, we know that x isn't false, so x is true. And we can keep going now. So we're going to branch on x being true. And it turns out this leads us to a contradiction immediately. So I'm going to write down not x. And I'm going to finish the proof with the empty clause. Okay. And I claim that this is somehow going to be considered to be a proof of unsatisfiability for this problem. So how do we do this? We need each backtrack clause to be easily verifiable. Okay. Now I claim that these backtrack clauses are something that we call reverse unit propagation clause. So what's the idea? We're going to take a new clause and we're going to assign it to false, and we're going to unit propagate. So we're going to say, okay, this clause, let's suppose this clause isn't true. Unit propagate it, and hopefully we reach contradiction. So I'm telling you that, okay, if you take this clause and unit propagate its negation, immediately it is obviously going to contradiction. So I claim that now it is safe to learn this clause to add it to our formula. Okay, because the contradiction, the negation of this clause immediately leads to a contradiction. So it's okay that we learn this clause. Okay. And I'm going to say, if this happens, that this is a reverse unit propagation clause. And it is a useful fact that if we run a DPLR algorithm with unit propagation, and we just output all of our backtrack clauses, then all of these clauses will be reverse unit propagation clauses. So this is a proof. Okay. If any of you know about CDCL SAT solvers, so this is how SAT solvers actually work in practice. They don't just do backtracking, they do conflict analysis. It turns out also that every learn clause generated by a CDCL solver is also a reverse unit propagation clause, a RUP clause. So I'll not go over this in detail, but an alternative proof of unsatisfiability. So the formula is just these three. We can work through end up with a contradiction clause again. So this is kind of why in the Boolean satisfiability community, reverse unit propagation clauses are the standard. It turns out it's very easy to take a SAT solver and just say, okay, whenever you learn something new, output it as a RUP clause, and then this will give you a proof. Some of you may have heard of the resolution proof system, which is possibly the standard way of reasoning about CNF formulae. So in resolution, we take the input as the axiom, and we have a single rule. So whenever we have a clause here, so we have some literals for C, and we have another clause which says not C or some literals, then we're just going to resolve on this C or not C, get rid of it, and end up with just the remaining literals is our proof set. And it turns out that and the idea here is to just resolve repeatedly until you reach the empty clause again. And it turns out there is a mechanical way of taking a RUP proof and turning it into a resolution proof if you want to do so. Very simple proofs is just one rule. What's the problem? Resolution can't count. So in the subgraph isomorphism problem, I want to tell you, okay, find this pattern graph that has n vertices inside this target graph that only has n minus 1 vertices. So this is obviously not going to work. You find me this big graph inside this little graph. Can't do it. In resolution, this requires exponential length proofs. This is not ideal if we want to make a subgraph solver output resolution proofs or even RUP proofs in the SAT setting. So it looks like we cannot just take SAT proof logging technology and reuse it straight away for subgraph problems. So what are we going to do? We might think, okay, we're going to need a proof system that knows what a graph is. It knows what the degree of a vertex is. It knows what connected means. It knows how long paths are and so on. I claim that we're not going to need this. All we need is a very slight increase in reasoning power, and then somehow magically we are going to be able to express all of the reasoning done by a very large number of state-of-the-art subgraph finding algorithms, still in an efficient way, and in a very simple proof system. So what are we going to do? First thing is we're going to stop using CNF, and we're going to start using pseudo-Boolean inequalities instead. So we have a set of 0, 1 variable values. I'm going to say that 1 means true. I'm going to write x bar of I to mean 1 minus x. So this is still negation. So this turns true into false and false into true. Constraints now are linear inequalities. So I'm going to sum up over some of my variables, multiply them by an integer constant, and say that they are greater than or equal to some integer. Yeah. Now, immediately I can rewrite CNF clauses to be pseudo-Boolean inequalities because, for example, x1 or not x2 or not x or x3 is the same as saying that x1 plus not x2 plus x3 is greater than or equal to 1. Okay. And instead of resolution, we're going to use cutting points as our proof system. So now we have a few more rules. We're allowed to assume that anything is in the input. And given any literal, so any variable or its negation, we can assume that it is greater than or equal to 0. So this is just saying, okay, we are working with 0, 1 value variables. Given any two constraints, I can add them together to create a new constraint. And this is a valid consequence of everything we know so far. I am allowed to multiply by a natural number. So this is just the same as adding a constraint to itself lots and lots of times, but slightly more efficient when we're talking about the length of the proof. And the final rule is the slightly interesting one, the division rule. I am allowed to take a constraint, and I am allowed to divide, and then round up all of the integers. And you will need to think hard to convince yourself that this round up all the integers step is in fact true. So what's the idea here? We can define reverse unit propagation in the pseudo-Boolean setting. It does the same thing as in the Boolean setting if we're working with clauses. It does something a bit more general if we're working with constraints. The idea here is now we're going to make proofs by using rep steps for backtracking exactly as before. But now I'm going to include some explicit cutting point steps inside the proof to do certain kinds of reasoning that are not easy to express in a reverse unit propagation setting. And it turns out there is already a verifier for this kind of proof. This is VeryPB, but people in this room might know a little bit about it by now. And I thought I would give you an example of actually writing a proof in practice for a maximum clique solver. So, how do maximum clique solvers work? Remember, we're trying to find a subset of vertices where everything in the subset is adjacent to everything else, and we want this to be as big as possible. Okay. So what does a clique solver do? It will pick some vertex B and branch on whether or not it wants to include this vertex. If I say, yes, I am including this vertex, I'm going to throw away everything that is not adjacent to me. Okay. And we're going to do this recursively until we can't branch any further. So, for example, if I say I am picking vertex 12, straight away we're throwing away every vertex except 1, 9, 7, and 6. Possibly then we recurse and say, okay, I'm also picking vertex 7. So we're only left with vertex 9 and vertex 6. And maybe I pick vertex 9. So I found through vertex clique. And what we're going to do is we're going to remember the largest clique we've found so far. And whenever I found, for example, a 3-vertex clique, I am only going to search for a 4-vertex clique or bigger. Once I find a 4-vertex clique, I'm only going to search for a 5-vertex clique or bigger, and so on. There's one more thing that clique solvers do that is quite useful. So a coloring of a graph, we give every vertex a color, and adjacent vertices have to be given a different color. And we could do this greedily or using some clever algorithm. I claim that if I can color a graph using k colors, it definitely can't have a clique with more than k vertices, because every vertex in a clique definitely has to be given a different color. Okay. Another way of looking at this is that a color class, so a set of vertices that all have the same color, describes an at most one constraint. So I can pick at most one blue vertex to go in a clique. I can pick at most one red vertex to go in a clique, and so on. Okay. So let's say we want to take our favorite clique solver and make it proof of. What do we do? First thing we need to do is describe the clique problem as a pseudo-Boolean problem. There are a lot of different standard file formats for clique solving, so we're going to have to deal with this. Then we're going to make the solver log its search tree. So we're going to output a small header. Every time we backtrack, we're going to output a rep statement. Every time we find a solution, I'm going to output a statement that says, hey, this is a solution, you should check this. And we're going to output a small footer to say at the end of a proof that I have finished the proof. We're going to try this and then we're going to see that it doesn't quite work and we're going to have to figure out what to do with the bouncer as well. And you may have noticed I'm going for a slightly different workflow. So we take an input, feed it into a solver and get out a result. And we're also going to get a proof. But rather than taking the input and the proof and feeding into the proof checker, we're going to cheat slightly and we're going to allow the solver to encode the input into pseudo-Boolean form because the proof checker does not know what a clique file is. So somehow this bit of the process, I've deliberately drawn it over to the left. This bit of the process is untrusted. So we want to keep this to be as simple as possible. And again, the checker is going to say yes or no. And this yes or no is now subject to the encoding being correct. So what is the encoding? I'm going to show you the encoding in the standard format for pseudo-Boolean problems, format called OPB. So the way we're reading this, tilde means negation. I'm going to say, okay, for any two vertices that are not adjacent, I'm going to say you can pick at most one of them. So, for example, x1 and x3, vertex 1 and vertex 3 are not adjacent. So I'm going to have the variable x1, which is true if vertex 1 is in the clique. I'm going to have the variable x3, which is true if vertex 3 is in the clique. And I'm going to say either x3 is false or x1 is false. And I'm going to do the same for every single edge. And then what I want to do is maximize the number of vertices which are true. It turns out the OPB format works only on minimization. So I'm going to minimize -1 times x1 plus -1 times x2 plus and so on up to x12. Okay. Is everybody happy that this encoding is correct? Probably as simple as mentioning.
There is no audio.
Right, disconnecting. Okay, we will switch to my laptop microphone. The audio might not be as good, I'm afraid. If I stand here, can you still hear me?
I think the sound is slightly worse, so maybe you want to be close to your laptop.
Okay. Let's see. Let's give this a go. I've lost my clicker.
There's something.
Chat says, okay, I'm back.
Yeah, I think we're good.
Okay. So, suitably improved in the very previous formats. We're going to start with the header line. So, 1.2 improved format. Very soon this will say 2.0. F41. So my OPB file has a total of 41 axioms. This F line just says, okay, what are the axioms? So what's that solver going to do? Maybe it's going to branch accepting vertex 12, accepting vertex 7, and accepting vertex 9. And we've found a maximal clique with 3 vertices at this point. I'm going to log this, and I'm going to say, okay, if I set variable 7, variable 9, and variable 12 to true, this is a valid solution. The optimal. The proof checker is going to check this, and it's going to say, yes, I agree. Now you only have to find a greater than or equal to 4 vertex. So it's going to change the objective for me. It's going to give me a new objective constraint saying, find something bigger. Now a solver might be in this state. It's accepted vertex 12 and vertex 9. It only has vertex 6 and vertex 9 now, that are feasible. And it's going to look at this and say, okay, I can't pick both 9 and 6 at the same time. I can color these the same color. So there is no greater than equal to 4 vertex, so I'm going to effectively this is then the
Because that's to go sensitive to whether you're talking into the laptop, unfortunately. So you're sort of drifting in and out.
Okay, I will try to stand here in the projector beam
and not talk too fast for you. Sorry about this. I'll have to check.
Okay. So we are backtracking from accepting 12 and 7. Now we're in a state we have accepted vertex 12, only 1, 6, and 9 remain as feasible. And again, obviously, we're not going to find a 4 clique here, so we're going to backtrack. Now we're back at the start. We're going to pick a different number. And then also accept at this point, we have vertices 1, 3, and 9 left. And again, to a solver, it's obvious. Okay, I can give vertex 1, 3, and 9 the same color. So there definitely can't be a 4 clique present here. So it's going to backtrack. We're now in this state. We have accepted vertex 11. We have 1, 3, 7, and 9 left. Again, we can 2-color this. So the clique we have has vertex 11 plus at most 2 other vertices. So we can't find a 4 clique. So we're going to backtrack. Now suppose we branch on accepting vertex 8, vertex 5, vertex 1, vertex 2. We have found a 4 clique. I am going to help you to prove that, yes, we have a 4 clique. The proof verifier is going to check that I have given it a feasible solution. And it's going to say, okay, now find me a 5 clique. Okay, maybe we're going to backtrack from having accepted 8 and 5. We only have 2 vertices left. We can't make 5 cliques using those vertices. Backtrack from vertex 8. And we're now back at the start with some vertices excluded. I claim that this graph is fairly easily 3-colorable. So the solver is going to backtrack. And we finish the proof with a contradiction. Okay. Everybody happy? Verity is not happy. So what happened here? I said we can backtrack from this state, and it is obvious. Verity looks at it and says, No, I don't agree that this is obvious. And if you check, actually, yes, this fact does not follow by reverse unit propagation. We were using a color bound, and it turns out, yeah, color bounds are not, they don't follow by reverse unit propagation. We can ask variability to give us a very verbose trace of what's going on. It doesn't really help us much in this case. So what's the problem? The color classes give us at most one constraint. At most one constraints do not follow by reverse unit propagation. So maybe we could take every single, excuse me, every single color class that we would ever use during a proof and just list them all as axioms in the input. I claim that this isn't really feasible and it's probably cheating. Okay. Instead, what we're going to do is we're going to recover color classes lazily. So, for example, x1, x6, and x9 are they're an independent set, so they can all be given the same color. We have this constraint that says we can't take both the vertex 1 and vertex 6, and another constraint that says we can't take vertex 1 and vertex 9, and another that says we can't take vertex 6 and vertex 9. I'm going to take all three of these, and I'm going to add them up to get 2x1 plus 2x6 plus 2x9 is greater than or equal to 3. Okay. Now I'm going to divide this whole thing by 2. This is where you can hopefully agree with me that the division rule is set. So 2x1 becomes x1, 2x6, sorry, 2 not x1 becomes not x1, 2 not x6 becomes not x6, 2 not x9 becomes not x9, 3 becomes 1.5, but we're dealing with integer variables, so I can round this up to 2. So I've derived that at least 2 of these have to be false, so at most one of them can be true. And it turns out that this process will generalize for arbitrarily large color classes, and it does it in an efficient way. And the nice thing is solvers don't need to understand cutting planes to write this proof. So you can take a solver and proof without understanding what the two is doing. Okay. This is what this looks like. We can take this proof and it passes through the verifier. Verifiably says verification succeeded. So if you trust the encoding, and if you trust that verifiably is correct, then I have shown that this input has a 4 vertex maximum clique. Okay. Is everybody happy so far?
Except with this sound, I wonder what would happen if you try to disconnect and connect with the. Okay.
How is that? That is better, I think. Okay. What does the virtual audience think?
Yes, I think it's better.
Okay, better. Fantastic. And I've lost my clicker. Okay. So it turns out this is a very general process. We can do this for basically every state-of-the-art clique algorithm in the literature at this point, including for the maximum weight clique problem as well. And this is kind of interesting, but people have spent a long time in developing a lot of clever techniques for practical clique finding algorithms. And somehow this cutting points process seems to be enough to justify all of this reasoning. Okay, I will not give you subgraph isomorphism in full, complete detail. Just to say we can do a similar process. We can encode subgraph isomorphism in pseudo-Boolean form, like this. And we can start doing lots of different kinds of reasoning. For example, if I'm trying to find this pattern on the left inside the target on the right,
I claim we cannot possibly map vertex P onto vertex T because vertex P has 3 neighbors, vertex T only has 2 neighbors, and we have to map all of the vertex's neighbors to different points. And it turns out this is also easy to justify in cutting points. I will not give you the full derivation, but very briefly, we have some constraints. We add them up. We add on the injectivity constraints. So we're adding up some at least 1 constraint, some at most 1 constraints. We tidy them up slightly, and we end up saying, okay, yes, you can't map this vertex to this place. In VeryPB, we can include explicit cutting plane steps to do this. And we can also do a lot of reasoning. Again, all of the reasoning that is done by state-of-the-art subgraph solvers. So they will reason about injectivity. They will reason about the distance between vertices. They will reason about the degrees of a vertex's neighbors. So this is called the neighborhood degree sequence. They will reason about the number of paths between vertices. There's this technique called supplemental graphs or shape graphs. It's a look where locally there are certain patterns that appear between vertices. All of this can be done efficiently in cutting planes. And somehow the length of the proof steps that we need to justify this reasoning are no worse than the time complexity of the algorithm that is doing the reasoning to find these facts out. And these proof steps only require trivial additional computations for the solver. This is interesting, and I don't think we really understand why. In particular, I spent a very long time developing a lot of these clever reasoning techniques for subgraph solvers, only to be told, oh yeah, this is easy, you can justify all this in cutting planes. That's, yeah, okay, maybe I wasn't as clever as I thought I was. So, okay, a few little things about proof system.
Maybe it's the cutting plane system that is clever, as you.
Maybe. It's only got 4 rules. It can't be, cutting planes can't be that clever. Well, okay, a few more things we're allowed to do in proofs. So I can pick some completely arbitrary constraint here. I pick a new variable A, and I want to introduce, okay, A is true if and only if this constraint holds. So if A is a new variable, it should be okay for me to do this. That this should not change whether or not the problem can be solved. Okay. So we can express this this verification using these 2 constraints. You can check this yourself. We have a rule in the proof system that allows us to do this and a few other things. Another thing we need to reason about is symmetries. Suppose I'm looking for this pattern graph inside a bigger graph. If a solution exists, then a solution where vertex C gets mapped to a lower numbered vertex than vertex D exists. Okay, the argument is just, okay, we have a symmetry. If you give me a solution where this does not hold, I can swap vertices C and D, and would be okay. It turns out that the VeryPB proof system lets us reason about this as well. One slightly more difficult rule, which turns out is a generalization of symmetries, is dominance. So I claim if we're trying to find a maximum clique in this graph, we can totally ignore vertex 2b. Why is this? So every vertex that is a neighbor of 2b is also a neighbor of vertex 2. So if you give me a solution that includes vertex 2b, I can make this into a solution which is at least as good by rejecting vertex 2b and putting in vertex 2 instead. So without loss of satisfaction, we can throw out vertex 2b. Okay. And again, it turns out we can do this in the proof system. Where have we come so far? So VeryPB can do reasoning about solving with symmetries, cardinality, XOR reasoning. It can do max-sat solving now for various max-sat algorithms. I believe Andy has uncovered several previously unknown bugs in state-of-the-art max-sat solvers that have existed for a very long time, but immediately became obvious when you turned on proof logging. We can't do hitting set max solvers yet because they use MIP solvers, and MIP solvers are black boxes. We have certified translations from pseudoboolean into CNF. We can do all sorts of subgraph finding algorithms, so clique, subgraph isomorphism, maximum common connected and diffuse subgraph. We can do constraint programming now with arbitrary integer variables. We have to do all 400 plus global constraints for constraint programming. That is Matthew's PhD. He graduates when he finishes all 400. So far we have, yeah. So we have, what do we have? We have absolute value, all different, Hamiltonian circuit, comparisons, elements, linear equalities and inequalities, minimum, maximum, regular, smart tables. And it turns out actually, if you have these, you can use these to create a lot more constraints. So we only have about another 200 constraints left to do. Work in progress. MIP pre-processing, I believe, is a thing. Dynamic programming works. I need to tidy the code up and then write this up. Yes.
So there's no proof logging MIP solvers?
I believe not. No.
Well, we've heard about LP solvers, I guess, but that's LP and it's also work in progress, maybe? Or maybe that's done, I don't know. But the same group in Berlin, are they working on something like that? Or?
There is proof logging for the open source MIP solver Skip being developed in Berlin. They have a proof system called Viper, I think. I think what they get to work now is, so one problematic thing with MIP solvers is that you need to do floating point for efficiency reason. I think they have proof logging only for the exact solver doing exact rational arithmetic, which incurs a significant slowdown, but not worse than an order of magnitude. But I think there are several, like the sophisticated techniques are hard to do. So you can do like I think a basic MIP solver, but like some of the advanced techniques that really drives the efficiency are missing. So it's more like a limited proof of concept for an exact solver, I believe. But I'm not fully up to date on state of the art.
Yeah. So some interesting questions. What reasoning can we justify? In particular, constraint programming solvers work by reasoning over hundreds of different kinds of inference algorithms simultaneously. Now, the theoreticians told me that, okay, you have extension variables, this A if and only if constraint rule. So this is as strong as extended Frege. So we know that extended Frege can simulate absolutely everything up to a polynomial factor, so you're good. Although they won't tell me what this polynomial factor is, and I suspect it's fairly large and unpleasant. Except then they told us that the dominance rule is even stronger than extended Frege. So maybe we're doing some kinds of reasoning that they haven't thought about yet. I don't know. Bigger question, what kind of reasoning can we justify efficiently? Quadratic overheads are really unpleasant when you're doing constraint solving. Cutting plane seems to be very good at efficient justifications for combinatorial arguments. We don't know why. How do we know the verifier is correct? We're working on it. We have most of the formally verified verifier now. How do we know the encoding is correct? We can do this for simple graph problems. For constraint programming, for example, that's a work in progress. How do we know the proof system is sound? Well, it turns out the formally verified verifier actually includes a proof that the proof system is sound as well, so we don't trust that. The proofs we produce can be really, 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 really big. A lot of the steps end up being redundant for the final proof. It would be nice to have a tool that takes a really, really, really big proof and shrinks it down a bit. Proof systems, they deal with unsatisfiability. So satisfiability is easy. I just give you a solution. Check it. Optimization, yeah, I just give you a solution and I prove that there's something better. That's not a big deal. If I want to enumerate all the solutions, well, I just give you a big list of solutions and then prove there aren't any others. Counting without enumerating, we have some ideas about that. That's work in progress. Can we take proofs from the solver and use them to understand why solvers work? This could be very, very interesting. This might tell us why solvers work so well when the theoreticians say that no, you can't possibly be this good. It can also tell us why solvers perform really badly when they shouldn't. For example, it told us why SAT solvers were bad at pigeonhole problems. Maybe this gives us something to do with explainability in the future. So, the propaganda, where we're at. We can verify solutions from state-of-the-art combinatorial solving algorithms, and we can do this in a unified proof system. We keep finding bugs in other people's solvers and our own, including inside algorithms that have been proved correct. I think at this point, not having either proof logging or formal verification should be considered socially unacceptable. So if you tell me I have an amazing new clique solver and it can't produce proofs, I don't believe your solver is correct anymore. I will ask fairly pointy questions in a review at this point saying, how do we know your solver is correct? Why should we trust you? Is testing it enough, etc. Hopefully in a few years, we will reach a point where if you don't produce proofs, then you won't be publishing. Honestly, the number of buggy solvers I've dealt with, I think this is necessary at this point. On a more positive note, if you do implement proof logging, maybe we can use this to help you make your solver better. So, if you want to join in, if you know anyone who's looking to start a PhD this October, get in touch with me very quickly. Glasgow has found some money left over that we need to spend. As soon as the paperwork is finished, I will be hiring for a 3-year postdoc position looking at analyzing proof logs. This will be in Glasgow, so keep an eye out for that. Send me an email if you're interested. You can install VeryPB, you can read its documentation, and we have a much longer tutorial on YouTube on how to write proofs. And I will stop there. Thank you.
Thank you, Ciaran. Questions from the audience? From the physical or virtual audience, or comments, complaints? So is there anything in constraint programming that you have been struggling with, or is it just the plain sailing these days? So one propagator at a time?
There are a lot of constraint programming propagators for machine scheduling that do all sorts of very crazy relaxations. And I don't understand how these propagators work. And it is not clear to me that we can implement these efficiently yet. I don't know. But people do entire PhDs on developing one new propagator for one new variant of this constraint. So that could take a while. It might be very easy. It might be completely impossible. I just don't know.
So we've done, let's say, very roughly similar things, not quite, but similar. And one thing that happened was that sometimes we saw, okay, these two techniques, once we have to boil them down to this sort of proof level, that they seem to be like the same thing, or there's an obvious generalization to both. But have you had experiences like that when you looked at, like, I don't know, propagator and so
Yes.
and do more than we've used before?
Yes, definitely. Propagators, a lot of them fall into a few different categories. So some propagators seem to be doing just a little bit of look ahead, but very efficiently. Some of them are doing this, okay, the network flow-based reasoning for accounting, cardinality, etc. Some of them are just reasoning about linear inequalities in a clever way. And we have kind of generalized techniques for doing each of these families of propagators. You could, in general, for example, for the flow algorithms, you could say, okay, give me this problem in full generality, and you end up with something called the global cardinality constraint. So people already know that this one exists. For table constraints, these are like DNS listed solutions. People have already generalized this to, okay, smart tables. What if we allow wildcards? What if we allow expressions inside tables? So I would say that this is something that the CP community has already been doing quite a bit. And proofs, they might uncover some new areas. On the other hand, already just talking about how we encode these constraints, for example, down to SAT, which is an established field, quite often reveals a lot of these similarities already. So I don't know whether we'll get anything amazingly new. Although I think the observation that propagators are really just doing a bit of look ahead a lot of the time might be not the way people think about things.
So if you want everybody to do proof logging, and you mentioned also that you were working on dynamic programming algorithms, which already then we're going down from NP hard problems down to polynomial time. So these are efficient algorithms. How do you think about dealing with the threshold? I mean, do I have to get a PhD in proof complexity first and learn cutting planes, or do you think the way to go is to somehow develop proof logging libraries, or is there some, how much does the normal person need to learn to actually do this?
So there are a few ways. So if you've got a good master's student, they can certainly do this work. You don't need a full PhD. Libraries can help. The other thing is we can say to people, okay, even if you don't have the hardest problem in the world, if you can easily put this inside a constraint solver, it will give you probably a fairly efficient algorithm for solving the problem, and it will give you proof for free. So encouraging people to use, for example, constraint programming even when they don't entirely need to, is a way of getting people to have proofs for free.
So what you're saying is your secret plan is not for proof logging to take over the world, but for constraint programming to take over the world?
Also that.
Also
yes.
that, okay. Okay, any other questions from the physical or virtual audience before we thank Ciaran again? So let's thank Ciaran. Thank you so much.